Okay, so last lesson we're already to figure out what is the moment of inertia of this composite beam is, right? By using the parallel axis theory. Okay, and then we can calculate the distance from the neutral axis to the top surface is 60 millimeter, and the distance from the neutral axis to the bottom surface, right, is the 100 millimeter. And we use the bending stress to calculate the compression and the tension, right, on the top and the bottom surface, right? Hey, so let's go back to the questions. Okay, so if we draw this beam is subjecting to the distributed load and the point load, right? And then we can plot it uh, to a free body diagram, right? And use the force balance. We use the force balance, okay? Sigma my equals to 0 and sigma fy equals to 0 because there's no force along the x direction. Therefore, we'd have to apply the equation sigma fx equal to 0. Okay, and then we figure out the moment at point A is 5K Newton meter, right? And the reaction at point A is 1K Newton. Okay, and then we can just roughly to draw the shear and bending moment diagram. Okay, so for this distributed load, you can see it's it's a plateau, right? It's a plateau, right? It's flat. And so we can take the integration of this distributed load, right? Convert it to the shear force. Therefore, when this plateau, after integration, it will become a linear relation, right? It will become a linear relation like this. And then if we continuously take the integration of this linear equation, it will become a second order, right? Second order equation, right? Right? Okay, so we already find the reaction at point A is -1. Okay, it's -1. Therefore, we can just plot our this initial. We can plot this reaction force at point A is -1K Newton, right? And then there's a slope, right? It's a linear relation, right? It should be at the point B, right? It should be at point B. And then the load between the point B and C, right? There's no any forces applied to it. Therefore, for the shear, it's a plateau, right? And then finally, there's a point load 2K Newton applied at point C. So for this shear diagram, it will return to 0. Okay, or return to 0. And also for the shear diagram between the point B and C is a plateau, right? So we take the integration, it will become a linear relation. Okay, become a linear relation. Okay, and the maximum moment, right, can be evaluated from this shear and bending moment diagram is minus 0.5 K Newton meter. Okay, 5.3 K Newton meter. Okay, I will tell you how to calculate it later. Okay, so, and then we can use the singularity function, okay, singularity function, okay. So we already know the distributed load W, okay, or some textbook will just write it as the Q of X. Well, the same thing, okay, the same thing. So you can just recap this singularity function from your materials mechanics books, okay? So this called the load intensity, okay, that's the force per unit length. It's 1.5, right? And x minus 0 is 0.8. So we suppose we define the coordinate 0 at 0.8. Okay, this is our origin right here. Okay, origin right here. Okay. Okay. It's power of 0 and minus 1.5, right? X minus 2 is at point B. Okay, point B. Okay, and we already know the shear force equals to the integration of the distributed load. Okay, the integration of the distributed load. Okay, sorry, it should be like this. Hold on, let me just slow down a little bit. Okay. Okay, so the shear force equals to the integration of the distributed load, or we say the load intensity, right? So we can take the integration of this term and this term, right? We got the 1.5 x minus 0, right, at point A, and with the power of 1, right, first order. And also we can take the integration, right? Just modify the order from 0 to 1, right? Okay. And also there's shear force from the reaction or the point load, right? So RA is the reaction applied to reaction at this point A, right? RA, right here is minus 1. Okay. Also it's 0, right? At this point A, we define it as the origin. And also there's the point load applied at the point C, right? 2, x minus 4, x minus 4. And always this last term can be ignored because x will equals to 4. Therefore, the last term becomes 0. Okay, becomes 0. Okay. And then we can rewrite this shear function. Okay. We can just rewrite this shear function like this. Sorry. Okay, like this. Okay, this is our shear function. So right now we have the our distributed load. We take the integration, we get the shear function, right? Right. And then we also know when we take the integration of the shear function, we will get the moment, right? So we take the integration, we get the moment. Take the integration of shear function, right? We get the moment function right here. Okay, and then we can keep going, taking the integration to get the slope. Okay, we're taking the integration of the moment over EI, right? We'll get the slope. Okay, and then we take the integration of the slope. We'll get a deflection. Okay, we'll get a deflection. Okay, so we got a slope and the deflection. Slope and deflection. Okay, and what I mentioned previously, the maximum moment is 5.3 when we calculate the area of this triangle. Okay, we can figure out the maximum moment from the shear and bending moment diagram. Okay, so after two integrations, we will get two constants, right? C1 and C2, right? And how to solve this C1, C2? From boundary condition, right? From boundary condition. Okay, so right now we can apply the boundary condition, right? So when x equals to 0, the slope equals to 0. When the x equal to 0, the deflection equal to 0, right? Okay. So we can find the value of C1 and C2 zeros, okay? Zeros. C1 equal to C2 equals to 0. Okay. Okay, so finally we can use this slope, the theta, or we say the y prime, right? Just plug in x equals to 4 because what the question asks is what's the slope at point C, right? So the point C is the distance equals to 4 from the point A, right? Therefore, we can figure out, oh, so at point C, the slope is minus 0.0082 radians. Of course, you can convert it into the angle, that's fine. So we know, oh, so there's a, right, there's a slope, right? There's a slope, theta. Or maybe my drawing is not quite correct. So I should draw like this way. It's the, right? So I don't know, maybe something like this. So it's the theta, the slope. Okay. Okay, so the first question we ask, what is the maximum stresses, right? So you can use the bending stress equation, okay, bending stress equation. And the second question asks the angle at free end C, right? We already figured out is the theta equals to minus 0.0082 radians. Okay, and what is the maximum stress? Okay, so if we just going back to its original shape of this composite beam. Okay, so the sigma S represent as the stress of the steel. Okay, the stress of the steel. Okay, the stress of the steel. Okay, and the factor n equals to 16, right? And we plug all this number here, we get the stress of the steel is 37.5 megapascal, which is the maximum tensile stress. So it's tension. It's the top surface. Okay, here. It's top surface. It's steel, right? It's steel. So its maximum stress is 37.5 megapascal in tension. Okay, so for this bottom part, the bottom part is composite of two materials, right? Wood and steel. So the stress for the wood, we still use the same equation, right? And plug all this number in this equation, we get minus 3.9 megapascal. Okay, and then we can use this value to compare with the ultimate tensile stress of the wood. Okay, and also the stress of the steel at the bottom part equals to n, because for steel we have to enlarge, we have to multiply the factor of n, right? Because we just enlarge the width, right, of the steel. And we plug all this number here, we get this value is the minus 62.5 megapascal. Okay, so which is the maximum compressive stress, and we can compare this value with the ultimate tensile stress of steel. Okay. Okay, so we have three values. One is right 37.5 tension minus 3.9 in compression and 62.5 megapar in compression. Okay, therefore for this for its top surface, 37.5 is the maximum tension. For the bottom surface, 62.5 as the maximum compressive stress. Okay. Okay, therefore you have to compare the its ultimate tensile stress of steel and wood to understand which portion might fail. They might fail. Okay. Okay, so let's just briefly recap a little bit. So for this shear and moment and its diagram, we can start from this equilibrium equation, right? Sigma F equals to 0 and sigma M equals to 0, right? And then we can draw the free body diagram of it. We can draw the free body diagram. Okay. And then if this beam is subjected to a distributed load, Q or W, or it's called the load intensity, which is the units of force per length. Okay, unit per length. So we know we can just take the integration, right? The integration, right? Sorry. We can take the integration, right, of shear, and we can take the integration of moment. Okay. Therefore, the change in shear from A to B, okay, is equal to the area of the loading diagram from XA to XB. And the change in moment from A to B is equal to the area of the shear force diagram between XA and XB. Okay. Integration, right? Okay, I think it's quite easy. We just recap a little bit from your materials mechanics book. Okay. Okay, this is one example. So it's quite simple, right? So in this case, it's only the point load. Okay, point load. R1 and 200 pound, 100 pound, and R2, right? So because it's all the forces are point load, right? Therefore, if we convert it into shear force diagram, it will be platoon only, right? Platoon, 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 right? And we take the integration of the shear, we get the slope, linear slope, slope, and slope. It's a minus because no, this shear force area is minus, right? Okay, so we can calculate the area. That's why I mentioned previously we can calculate the area, right? This area we are equals to the value of the moment at this point. Okay, at this point. Okay, at this point. Okay, so what is the maximum moment? It's right here, right? And then we just plus the sorry, just plus the area from this shear force diagram, right? Okay, so area 1 plus area 2 equals to area 1 plus area 2, right? Equals to this point. Okay. Okay, so the singularity function, you have to remember this for sure. Okay, so in the case of the beam is subjected to the concentrated moment. Okay, so we can write its singularity function in the term of this, right? And if we take the integration of the singularity function, we will just right, we just multiply its order will be modified to -1 from -2. Okay. And if this beam is subjected to the point load, or we say the concentrated force, we can regard it as its singularity function as the unit step function, unipause function. Okay, so it will be like this x minus 1 power of -1. And if we take the integration of this equation, so its order will be modified to 0, right? And if this beam is subjected to a distributed load, right? It's a distributed load with a unit step function. Okay, so it should be regarded as the distributed load like this way. Okay, so whose singularity function is x minus a, the distance from the start point of the distributed load with the power of 0, right? Okay. And if x is smaller than a, point A, and the value of this equation equals to 0, and if it's greater than a, the value of this equation equals to 1, right? So we take the integration of this singularity function, we get its power will become 1. Okay, it will become 1. Okay, and if this distributed load is a ramp function, if this distributed load is a ramp function like this, okay, so we can just write its function like its singularity function is like this, power of 1. Okay, it's power of 1. Okay, so if this distributed load is a ramp function, so we can define its singularity function is power of 1. Okay, and if we take the derivative of this ramp function, right, it will become the power of 2, okay, over 2, okay, over 2, right? Is that clear? So this table just briefly summarize the singularity function for each loading condition, okay, loading condition. Okay, so there's one example, so I just skip this, okay? So it's quite easy, so just skip this. So I'm gonna show you the example for the bending deflection, okay? So if there's a beam is subjected to the point load and the distributed load, okay? And its Young's modulus is 12 GPa, and the cross section is 150 millimeter and 50 millimeter. And what's the slope at point A? And what's the deflection at point C? Point C is right here, point A is right here. Okay. Okay, so we know the process for the singularity function, right? We already know the process of the singularity function from its distributed load. Take the integration, we got a shear. And integration, we got the moment. And take the integration, we got the slope. And take the integration, we got the deflection. Okay, the deflection. Okay, and then we calculate the its moment of inertia, the second moment of inertia, right? And we figure out what is EI is, just right, just we calculate the I value times the Young's modulus, right? Okay. Okay, so and then we draw the free body diagram. We can regard this distributed load as the point load, and then we use the equilibrium equation to figure out the reaction at point A is 4.25. It's 4.25. Okay, the same thing, right? That's what I mentioned. The distributed load, right? Its load intensity is 5 kN over m. It's 5 kN per meter, right? So it's the starting point is right here, right? At point C is 1, right? Because 0.5 and 0.5. Okay. Okay. And we don't have to take into account the last term, right? Right here is 0. Okay. Okay, and then we can take the integration to get the shear force, right? To get the shear. Okay, and then remember there's still the point load applied. Okay, there's still the point load applied. Okay, previously we already calculated, right? For 0.25 at 0.8, right? For 0.25 right here, RA, right? Right here. And the other point load is 4, right? It's 4, right? Because of the point load, its power of the singular velocity function is 0 minus 0.5 right here, right? 0.5. Okay, and then we can take the integration of the shear equation to get the moment. Take the integration of this equation, we can get the moment, right? And we take the integration of the moment, we get the slope. And we take the integration, we get a deflection, right? After the two integrations, there are two constants, C1 and C2, right? And then we use the boundary condition. We use the boundary condition. One is x equals to 0 at point A. The deflection equals to 0. And the x equals to 2. That's mean at point D. That's point D and point A, right? The same thing at point D, its deflection is 0, right? And then we can figure out C2 equals to 0 and C1 equals to minus 1.604. Okay. Okay, so we finally got these two constants, and we want to figure out what's the deflection at point C, right? So we use the delta x, this equation, and when x equals to 1, plug x equal to 1 in this equation, you can figure out, oh, so the deflection at point C is minus 5.8 millimeter. Okay, minus 5.8 millimeter. Right? So, and oh, sorry, I forgot one value is the slope, the angle at point A, right? When it's deflected, there's an angle right here, theta here, slope here, right? So we use the this equation, plug x equals to 0. We get that this angle equals to minus 9.51 times 10 to power of minus 3 radius. Okay, radius. So we figure out what's the angle or what the slope is at point A and what the deflection is at point C. Okay. Okay, so that's the brief summary. We already know the forces or loading condition. One is the axial loading and torsion and bending, right? We know the axial loading whose stress is the force divided by area. Its elongation is equal to PL over AE. For the torsion, the shear stress is the TC, torque times the C is the distance from the neutral axis to the top or bottom surface, okay, divided by J. J is the polar moment, right? And the twist of angle equals to TL over JG. G is the shear rigidity. And for the bending stress equals to MY over I, right? And we can figure out what the shear and the moment is, and we keep taking the integration, we get the slope and the deflection. Okay, slope and deflection. Okay. Okay, so what's next? Next is called the transverse shear. Transverse shear. Okay, there are two conditions. One is that if we have the beam, which is composed of layer by layer with many plates, okay, many plates, and if this plate, and this plates, there's without any bonding, okay, we just stack these plates, just stack them together. Okay, in this case, if we apply a force, what we get? If we look at this small element, what's the condition, or what's the stress condition of this small element? Well, in this case, this small element only the shear at this surface. Okay, so there's no shear. So in this case, there's only the shear here and here, and there's no shear force right here. Okay, because for in this case, the interface between each plates, we can assume it's as the it can slide with each other, right? So when we apply the point load, so plate and plate in between a slide, okay? And the second case is that we still have the plate stacked to each other, and we just constrain, okay? We just constrain each plate, or we say we just stick the plates with each other tightly, stick plate and stick with strong glue or something, just stick them together. And then we apply the load. What's the situation we have to consider if we have say we have a small element? So in this case, there's a shear between the plates, right? There's a shear right here between the plates, right? Oh, sorry, not at this point, sorry. Not here. Okay. So we have the shear in between plates, right? In this case. Okay, so what's this shear called? This is shear called the transverse shear. It's called the transverse shear. Okay, transverse shear. Okay, so let's look into some the real case. Okay, suppose we have the beam like this, right? The beam like this. Okay, it's cross section. Here is this cross section, and there's distributed load applied, right? And here is this neutral axis. Okay, neutral axis, and we define the coordinates. Y1 is the distance above the neutral axis. Okay, so this beam is subjected to distributed load and the point load or concentrated load, right? And if just look into a small element right here, if we look into the small element, infinitesimal point or element, right? So we just look into here. What we get? What we get? Or say we can remove one part from this beam. Okay, what we get? So because this beam is subjected to bending, right? From this distributed load and the point load. will cause this beam bent, right? So the bending stress applied, right? The bending stress, of course. The bending stress is cause the shear and shear, right? Of course, there's some distributing load applied on the top surface. Okay, in top surface. So if we plot the force equilibrium equation, we still need a shear to balance this element. Okay, delta H. Okay, delta H. Okay, delta H. So we can define the shear. This shear is called the transverse shear stress, equals to the shear force, right? Right here, shear force divided by the shear area, right here. Okay, right here. Right? So the shear area equals to delta X times T, the width of the beam, right? So the delta X is fixed and the T is a variable because this value is gonna be changed depending on Y1, right? Depending on Y1. Okay. Okay, so this is what I mentioned previous slides. We can use the sigma F X equals to 0 of this free body diagram, right? To find out what's the delta H is. Okay, so I'm gonna skip those maths. You can just figure out by yourself. So and finally we get the shear force equals to MC minus MD over I, right? And the last term right here, we define it as the first moment of area Q, right? The second moment of area is what? I, right? It's the I value. Okay, so the definition of the first moment of area is the AS times the Y bar. Y bar is the distance from part of this cross section, the centroid of the part of this cross section to the neutral axis, okay, Y bar. And this AS is the surface of the transverse shear stress applied. So it's in this case it's delta X times the thickness T. Okay, right here. Okay. So if we focus on the cross section, there's a shear force applied to this cross section, right? No matter what's the shape of it. Okay. Either it's the rectangular or this round shape like this. Doesn't matter. Okay. So the transverse shear equals to the shear force divided by the shear area applied to this plane. Okay. Okay. So, and the AS equals to delta X times T, right? The thickness. Right? And the delta H is the shear force applied to the AS. Right? Is that clear? And the distance is from the centroid of the top part to the neutral axis. And I is the second moment of the area of this whole cross section. It's a whole cross section. Right? So we can just convert this shear stress, or also says this is a transverse shear equals to the shear stress shear force divided by the AS and equals to the delta M times the Q over I times X times the AS, right? Delta X times T. Right? So from this previous slide, we already know that delta H equals to delta M over I times Q, right? Right? So here we can just replace this term. right? With for this delta H. And we can just rearrange it, right, to get this term. Okay. And then we can define the dm dx. Dm dx is the shear force. Is the shear force applied to this whole cross section. The whole cross section. Okay. Okay, so let's have this one examples here. So suppose we have this I-beam, whether it can hold or not with a glue whose maximum shear stress is 200 kPa. So what's that mean? That means you have three components, 1, 2, and 3, right? And each of it is stick with glue here. Okay, with glue here. And we know its neutral axis, and we know the dimension. So in this case, because the different parts stick with glue, right? So there must be a shear, transverse shear occur between the surface, right? Between the surface. And we already know the transverse shear equation, tau equals to V times the Q divided by IT, right? Okay. And this is a cross section, and this beam, this I beam, is subjected to the 1 kilonewton, and with 2 reaction 5 Newton each at 2 endpoints. At 2 endpoints. Okay. Okay, and this I beam is composed of 3 parts by glue connected, right? By glue stick with each other, right? Therefore, I have 3, 1, 2, right? And 3, right? 1, 2, and 3. Oh, sorry. We should say we use the subtraction, but not the summation. Okay, so we have this whole beam without any just have a solid beam, rectangular beam, right? We have this whole beam like this. Okay, and then we have to subtract it, these 2 parts right here, this part and this part. Okay, we have to subtract it, these 2 parts. Okay, to calculate its segment of the area, right? So the I equals to is the for this rectangular solid beam minus 2 rectangular, right? Equals to 1.6 times 10 to minus 5. Okay, and then we know the shear, right? The shear force applied to this cross section equals to 5 Newton, right? From this shear force diagram. Therefore, the Q, okay, the first moment of area is AS times Y bar. Y bar is the distance from the centroid to the neutral axis, right? So the Y bar is 10 plus 50. 50 is the distance from the neutral axis to the bottom surface of the top part, right? Top part of the beam, right? And there's a 10 as from the bottom to the centroid. The centroid is 10. Therefore, the distance from the neutral axis to the centroid is 10 plus 50. Okay? Okay. And so we can plug those number in this Q, right? We can plug those number here, right? In this equation, and we got the tau is 185 kPa, and 185 kPa is smaller than 2 kPa. 200 kPa. Therefore, this glue to stick each beam is safe, right? It's safe. It's not going to be delaminate. It's not going to be delaminate. Okay. Okay, so we know that for the bending stress, the maximum stress should be located at the top surface or the bottom surface, either is tension or compression. However, for the transverse shear in the interface, the maximum transverse shear should occur at the center, and it should be zero at the top and bottom surface. Okay. Well, just some math work, you can work on it. I mean, I think it's not quite important. Basically, we just have to remember this final equation. That will be fine. Okay, so you can check the textbook or tables where it tells you where is the maximum transverse shear stress is with different cross section. Okay, with different cross section. Okay, so for the cantilever beam, the rectangular cross section, the maximum shear, including the bending and the transverse shear, we are equals to this equation. This equation is from the Moore's law. Remember that from the Moore's circle, but not Moore's law. The Moore's circle, right? From the Moore's circle, we calculate the maximum shear stress, right? So we plug those dimension and the force in, can find this equation, right? And the h is the height of the beam, and the b is the width. The l is the length of the beam, right? And the y is the distance above the neutral axis, and the c is the distance from the neutral axis to the top surface or the bottom surface. Okay. So from the previous equation, we can find the relation between the maximum shear stress, which is including the bending and the transverse shear, with the geometric, or we say geometric ratio L over H. So what's this figure tells us? So when L over H equals to 1, 1.5, 2, 2.5, 3, and so on. So what we discover? We discover when this ratio Y over C equals to 1, right? It always has the highest value of the maximum shear stress compared to other ratio. That means the maximum shear stress will be located at the top surface, right? Because 1 over C equals to 1, right? Even the ratio is 2.5 to 1/3, right? So this right? Even somewhere within this beam, right? Somewhere within the beam. Okay. So what this information tells us, if this ratio, the L over H, reaches the critical point, is say it's 0.5. So suppose we have the ratio, say it's 0.25. What we get. So the situation is different, right? So when the Y over C equals to 1, which is smaller than others, right? Smaller than others. So when this ratio equals to 0.5, what that mean? That means we get a critical value of the maximum shear stress. That means this dimension is independent. Always say the maximum shear stress is independent of this ratio, L over H. Okay, when this ratio is greater than 0.5, right? The Y, the higher L over H ratio, we'll get the higher maximum shear stress, right? And when this location close to the top surface, we get a higher maximum shear stress, right? However, when this L over H ratio is below 0.5, right? So it's a change, right? A change. Okay, so or we can say when this ratio is greater than 0.5, the bending stress maybe dominates this maximum shear stress. Okay, when this ratio equals to 0.5, it doesn't matter. I mean, it's the constant, it's fixed, right? Okay, so what's the meaning of the y over c equals to 0? That's mean the neutral axis, right? So we can realize that at this point, what's this stress dominant should be? This should be the maximum transverse shear stress, right? Because we know the maximum transverse shear stress occur at the location at the neutral axis. However, for the bending stress, whose maximum bending stress is located at the top surface or the bottom surface, right? So we can say this point is the maximum transverse shear stress. Okay, and this point. Okay. So you guys must clear with that. Okay, so due to bending outer surface, when y over c equals to 1, where the transverse shear is 0, right? And y over c equals to 0, where the bending stress is 0. Okay, so I already described this previously. Okay, so it is those this figure is used for the round or rectangular solid, okay, but not for the I-beam or the channels. Okay, it's only for solid. Okay, it's only for solid. Okay, so this part of the transverse shear will be ended here and stop here. And next lesson, I'm gonna focus on the stress element analysis and the how to plot the Morse circle and how to use Morse circle to figure out what is principal stresses is and the maximum shear stresses is in 2D or 3D elements. Okay, so we'll stop here.